Today's notes are going to be about
E.
shout out to my daughter Brooklyn for helping us out with the notes for today. So I wanted to start with an intro to what this number E is. You're actually going to learn more about it in future math classes, but today I'm just going to introduce this idea to you. I am totally going upstairs right now because my children are very loud and are screaming about everything. So today, to intro this topic, there is a link in Schoology, and if you open it up, you'll see that there is this part within the link where it talks about compounding interest. Now, we've looked at this topic already, this idea of the more times you collect interest, the higher amount of money you'll end with. Now, if you look at this scenario, it says that you're given 100% interest, which would be unheard of, on $1. So if you think about it, at the end of a year, you would have $2. But if we collected interest twice a year, you end with $2.25. And again, this goes through that idea that you're earning interest on your interest. So that halfway point, you had $1.50, but now when you collect the remaining 50%, you end up with a higher amount. Now, if you do this quarterly, we can talk about how you end up with even more. And then they did an example where they did 10 times a year. Now, you may question, well, why wouldn't we collect interest every second of every day? Because wouldn't you have this infinite amount of growth in your money? And actually, you wouldn't. Eventually, this converges to a value, and you'll see that that value is 2.718. So no matter how many times they collect interest, let's just say it was 300 times a year, 400 times a year, 1,000,000 times a year, you're going to see that the end amount of it would actually be this value of 2.718. Now, we have a special name for that value of 2.718, and we call it E. For right now, we'll be using, and it looks like a variable, this idea of E, and we're not going to fill in 2.718 each time. We're going to use E in place of that. So if you go to today's notes, you'll see that that's basically what this table's talking about, this idea of approaching this value of E. Now, E, just like pi, is an irrational number. So it just keeps going. It's not just 2.718. There's more decimals to that. And it's just like pi, because you know how pi does that same thing, 3.14, and then keeps going. If interest is compounded continuously, you want to look for this word continuously. There's a formula we're going to use that involves E, and I'll show that to you momentarily. We're going to graph today with this base of E, and you're going to see that because E represents approximately 2.718, these are always going to be growth functions unless they've been reflected. So in order to do today's notes, I'm just going to recall that formula for compound interest, and it's actually up here in a sense, but we don't have the time. So remember, for collecting interest using that compound formula, you can do y equals, or a equals, the starting amount, 1 plus the rate, divided by the number of times we collect interest, all raised to the n times t power, or x, whatever variable you want to use. Well, today's new formula is this idea of continuously. So if you ever see the word continuously, we're going to still start with y equals, and then that starting amount, but in place of this 1 plus r over n, we're going to actually put E. And then we're going to raise this to the rate times time. So how do we use this formula? Well, you're going to see problems that say compounded continuously. The second you see that, right away, think this formula, and a lot of times you'll hear people refer to it as PERT, P-E raised to the R-T. So if I want to find out how much the investment is worth in 4 years, well, I am going to, again, start with this y equals 1,000, but in place of the 1 plus, I'm putting E to the rate times time. Well, in this case, the rate is 0.05, and then the time is for 4 years. So we can go to our calculators, and we can type this in. Now, when you type this into your calculator, 1,000 There's actually two different buttons you can use for E. I think the best one is, oh, I can't zoom into my calculator. Oh, yeah, I can. This one right here above this LN button, there's an E and it has a little exponent that comes with it when you hit it. So what we need to do is delete what I just did and hit second, and then that button that has that E to the X above it, and then you can fill in 0.05 times 4. Now, if you have a calculator like mine and it goes straight to the exponent, you're good to hit enter. But if not, you need these parentheses around the exponent. So check to see that you get the same answer as I do. And if you do, then that means you typed it in the right way. Now, keep in mind, if I did the same problem, but I used the other formula and I compounded the interest monthly, you would see that the amount would be very close to this, but this answer would be higher. Whenever you compound continuously, you end up with a larger amount on that same situation. Now, for part B of this, it says, when will it be worth $1,500? This is exactly what we did with the other notes with where we used our calculator. We're going to let the left-hand side be 1,500 and the right-hand side be this 1,000 E and then 0.05. But remember, we're going to use a variable here, so X or T, but we want to make sure we're finding the time at which this happens. So in your calculator, you can go to your Y equals. Remember, we make this Y1, we make this Y2, and we want to find where these intersect. So we get that, we get this, and then that E button, and then 0.05, and then X. Again, don't forget to use parentheses if you have a calculator that does not put it in the exponent. Now, before you hit graph, we have to change our window. So go to your window. Keep in mind that X is the amount of time. So for right now, I'm going to try 0 to 10. You might even want to go 20 just to be safe. 20 years it might take. I don't think so. I think this is going to happen pretty fast. But if you want to just be safe, remember though, your Y values have to show this number. So I'm going to say 0 to 2,000 just to make sure I can see that number. And then I can go to graph. Oh, no. Whenever this happens, I have to restart my calculator because it doesn't give me the right answer. It's like glitching. So let me very quickly restart this and do this again. I'm sorry. You can fast forward a little bit till you get to the answer. 1,500 and then 1,000 E to the 0.05 X power. Oops, don't need that. And then go to my window, and again, 0 to 20, and then 0 to 2,000. Sorry about that. So then, yeah, now it's not glitching, so we're good. So you want to find where these two intersect. So what you can do now is go to that second, I'll write it down, second button, and then you want to hit trace up at the top. And then we want to do option 5, intersect, and then hit enter 3 times. Oops, we meant to do that. So we get X is approximately 8 point, does it say how to round? It does not, so we'll go 8.1 years. So that is how you use this new formula. So just keep an eye out for that word continuously. And then the final topic we're going to look at is how to graph these. This is identical to what we've been doing with growth and decay functions. You're just typing in something that is a different function. So if you go to Y equals and we clear out what's there, we will do this first example, E to the X. All you have to do is second, and then that same button as before, type in an X. Let's change our window. Let's go to zoom and do standard. And then you're going to see this basic function for E to the X. And note that it does look just like an exponential growth function. So if we're graphing this, you're going to go to that table of values. Obviously, you're going to see a lot of decimals. Just keep in mind that as you go to the left, I was noticing in some of your graphs that you submitted to me through the homework that you made your graph just stop at like that value, but just keep in mind you do need to keep it going and hovering above that asymptote, because notice that these values do keep going. They just keep getting smaller and smaller. So a good number of you guys had just stopped, but you need to show me that flattening out of the line. At 0, we have a value of 1. And then it looks like by 3, we're already off the graph. So at 2, I'll get this value approximately here. But by the time you get to 3, you should be off of your graph. Just think about this. This value for E is really 2.718. So it's going to grow very fast. It's like tripling something every time we change our X value. So to answer the questions on the side, you will see the same things that we saw from yesterday or from the other day of notes. X-intercept, there's none for this one, but there was that Y-intercept of 0, 1. As with the other graphs, the domain is always all real numbers, but the range depends on that asymptote. Because we have this asymptote right here, you can see the graph flattens out at that value on the left-hand side. We are either going to be entirely above that asymptote or entirely below. So because in this situation we're entirely above, we're going to say that our range is from 0 to infinity, and then that asymptote is at y equals 0. So I'll do one more with you guys, and then I want you to try the question number 4 on your own and then check the key to make sure you got this. Question number 3 is the same idea. Now keep in mind, we're just going to take the graph from number 2, the parent function, and really think about the transformations to this function right here. We would have a horizontal shift to the left 1, and then a vertical shift down 4. So technically, if you want to copy and paste the graph from above and move everything to the left 1 down 4, you can. I will do that, but I also want to show you this in the calculator as well. So if I paste this, this is where we would be with the parent function. Note that if I go to the left 1 and then down 1, 2, 3, 4, this is where my graph would end. Now note, as I've talked about before, that this shift is going to be the horizontal asymptote value. And what I like is how I had copy and pasted the parent function, and you saw how that horizontal asymptote moved with the transformations. It wasn't affected by the shift to the left, but it was affected by that shift down, which is why that value becomes our horizontal asymptote. Now, obviously, we can still type this in and confirm these things. So if you go to your equation, we technically already have e to the x in there, but we can add in that plus 1, and then we can put that minus 4, and you're going to see that it moves exactly the way we had just seen it move. You can even go to the table, and you can confirm those points. So second table, and you can see that that one key point, that -1, -3, landed on our graph. Now, to answer the questions on the side, we do have an issue because if you go to the graph, there's an x-intercept, but that x-intercept does not appear to be a nice value. So remember, we have to go to second, trace, and then find that 0. Left bound be below the x-axis, and then right bound be above. Enter one more time for guess. And you should be getting approximately 0.386, comma 0. Oh, it said round to the nearest hundredth, so let's try that again, 0.3. There you go. Y-intercept, it does have one. It doesn't look nice. If you trace 0, you will get that the y-intercept is 0, -1.28. So remember, for x-intercepts, you have to use the 0 option. For y-intercepts, you're going to trace x equals 0, or just look at your table. Domain is always all real numbers. Range is always dependent on that asymptote. Because that shift 4 down brought that asymptote to y equals -4. We did not reflect the graph in any way, so our range is still going to be above that asymptote value. So I hope you guys feel good with this topic. Please make sure you are practicing. Obviously, do number 4, check with the key, and then I'll have obviously future practice to make sure you guys are feeling good with all of that.